So I'm going to present my second year paper. The name is Mechanism Design with Stopping Problem. So I will introduce the general problem first. So the general problem that I want to investigate is you have an agent who observes a Markov stochastic process, and the agent chooses two things. One is when to stop, and we call it tau, and the other thing is after the agent stops, what action to choose, say qt in some set q. And the principal for each q would pay differently at different times. So it's a pt as a function of qt. It's different for each t. And the question to ask is what kind of behavior is implementable. So I'll give two examples first, and then I will introduce the model formally. So the first example that I want to give is the investment example, where the agent collects information about the value of a project. Say the valuation is xt, and the agent keeps collecting information until some time tau, and then the agent, when he stops, she would decide how much to invest. It might be money or effort, and then the problem is the principal wants to implement a particular stopping rule by paying the agent some pt as a function of qt. The reason why he wants to do that is the principal may possibly have different preferences on the amount of information to collect or the amount of investment. The second example I'm going to give is called the advice example, where there is a unknown state theta. It's either -1 or 1. I will tell you why it's not 0 and 1 later. And the payoff should be linear in the state in this example, and the agent has private information in the form of a belief of the state, which is denoted by xt, and the agent would recommend an action. The agent gives one of two possible recommendations. One is canceling the project. The second one is starting production, and let's call it -1, 1. Or the agent could continue research, basically means wait until the next period. And what the principal wants to do here is the principal wants to set a price so that it can incentivize the agent to provide an advice that aligns with the preference of the principal. So it may be biased, but basically I'm choosing prices for each advice to incentivize the agent to choose the one. Basically, let the agent tell me what the state he believes is in. So now I will briefly talk about the formal model. So the agent's problem here is she observes a Markov process. Each at each time it takes value in some compact set, say a closed interval from x lower bar to x top bar, and then the agent chooses a stopping rule plus a terminal action called tau and q combined, where tau is a stopping rule. It maps from the stochastic process to a stopping time. It is what I call a predictable stopping rule, means she can only use information before she stops, and she cannot use information after she stops. That's what predictable means. And Q is mapping from the valuation to the set of possible terminal actions. Could be continuous or discrete. We will use continuous here. And the agent maximizes some form of utility, which is the expected value of the utility at the stopping time, subtracted by the transfer or the prices. And then the principal here observes the time of the decision, which is the stopping time, and the actual decision at the stopping time, not the other decisions. And the principal chooses a mechanism or a set of prices to incentivize the agent to use a particular stopping rule decision pair. And here we call this thing is implementable, means given the prices, the agent's optimal stopping rule plus terminal decision is this thing. And now let me introduce some of the important utility functions. So first is the stopping utility, or the stopping value here, which is the max over all possible alternatives subtracted by the prices. of the utilities subtracted by the prices. The other one is probably the value function. So value function is the max between the stopping value and if the value function, if we continue to the next time, so it's the expected value from the next time's value function, which we go back and call it the continuation value. Basically, we can rewrite the continuation value here as the soup of all the future expected utility. But let me show you the diagram, which makes it a lot more clear. No, I will give the two of the interesting stopping rule first. One of them is the single stopping rule, which here is the minimum when x is above some threshold. So the bt are changing over t, and it's basically some kind of threshold. And the idea of the single cutoff stopping rule is basically the agent will stop after he gets above some threshold. And the binary cutoff one is the same. So if the agent gets outside of this two threshold of the boundaries, then he or she stops. If it's inside, then he continues. And diagrammatically it's like this. So if ut is above, so ut is the one on top. I mean the ut is the blue one, which is on top on the right. Then we stop on the right and we continue on the left. Similarly, if we have for the binary ones, if it's outside, we have blue line above the black line, so we stop. Inside we have black line above blue line, so we continue. So the next thing I want to talk about is some of the assumptions on the stochastic process. So the stochastic process needs to be Markov. It needs to have monotonic transition and continuous transition, and these two means the conditional expectation operator on these things would preserve monotonicity and continuity. So basically, if you have a monotonic function, then if you take expectation conditional on the previous period's evaluation, then you still would have a monotonic function, and similarly, it maps continuous to continuous functions. And it should have full support as well. And in some example, I will assume martingale too. And two examples that we will have, two examples of stochastic processes that satisfy all these four conditions would be additive and multiplicative random walks. And the proofs was given in a paper by Cruz and Strack, in 2014, which is the next thing that I will talk about.